It's October 1942, Wright Field, Dayton, Ohio. Another B-17 flying fortress comes screaming down onto the runway, landing gear up, sparks flying as metal scrapes concrete. The bomber skids, collapses, grinds to a halt. Fuel ignites, flames consume the fuselage. Ground crews sprint toward the wreckage, fire extinguishers ready, but they already know what they'll find. Another 10 highly trained airmen, dead. Not over Germany, not shot down by Messerschmitts, dead on their own airfield in Ohio, killed by a mistake that should never have happened. And this wasn't an isolated incident. Across America's training bases, B-17s, B-25s, and P-47s were crashing with alarming frequency. Pilots were retracting their landing gear instead of adjusting their flaps. Experienced aviators, men who'd flown hundreds of hours, were making the same fatal error over and over. The Army Air Forces were desperate. They blamed the pilots. They intensified training. They threatened disciplinary action. Nothing worked. The crashes continued. And then a 25-year-old psychology student, fresh out of Yale, walked into the Aero Medical Laboratory at Wright Field and solved the problem in less than a week. His solution cost almost nothing, could be implemented immediately, and worked so perfectly that accidents dropped to zero overnight. His name was Alphonse Chapanis, and his simple innovation didn't just save hundreds of bomber crews during World War II. It changed the entire way we design machines, and his principles are still used in every aircraft cockpit, every car, every piece of technology you touch today. This is his story. Before we dive in, if you enjoy deep dives into incredible World War II stories that changed history, hit that like button and subscribe. These stories take weeks of research to get right, and your support makes them possible. Alphonse Chapanis was born on March 17, 1917, in Meriden, Connecticut. His parents, Anikadas and Mary Chapanis, were immigrants who valued education above almost everything else. Young Alphonse, called Al by friends, showed an early fascination with how things worked. Not just mechanical things, but people. He'd watch how his classmates solved problems, how they interacted with tools, how they made decisions under pressure. In high school, he excelled in science and mathematics, but it was psychology that truly captured his imagination. The human mind, he realized, was the most complex machine of all. He earned his bachelor's degree from the University of Connecticut in 1937. His senior thesis caught the attention of prominent psychologist Walter Miles at Yale University, who offered him an assistantship. Miles was working on physiological psychology, studying vision and perception, and he saw something special in the young man from Connecticut. Chapanis moved to New Haven and threw himself into graduate work. He completed his Master of Arts in 1942, focusing on experimental psychology and vision research. But this was wartime. America and the world was changing fast. In the autumn of 1942, while finishing his doctoral dissertation, Chapanis received his commission as a second lieutenant in the United States Army Air Corps. He was sent to Texas for training as an aviation physiologist. The timing was extraordinary. His major professor, Walter Miles, had arranged something unprecedented. Chapanis would become the first military research psychologist ever assigned to the Aero Medical Laboratory at Wright Field in Dayton, Ohio. He completed his PhD from Yale in February 1943 and immediately reported for duty. Wright Field in 1943 was organized chaos. The facility had grown from a sleepy experimental station to the nerve center of America's aviation research and development. Hundreds of aircraft landed and took off every day. Mechanics swarmed over bombers, fighters, and transports, testing modifications, running experiments, pushing the limits of what these machines could do. And they were crashing. A lot. By the time Lieutenant Chapanis arrived, the pattern was unmistakable. B-17 flying fortresses, the pride of the Army Air Forces, were experiencing what investigators called wheels-up landings at an alarming rate. A pilot would bring his bomber in for what should be a routine landing. Everything perfect. Approach speed good, altitude correct. The bomber settles toward the runway. The pilot reaches for the control to adjust his wing flaps, those movable surfaces on the trailing edge of the wing that help slow the aircraft and increase lift at low speeds. But instead of lowering the flaps, the pilot retracts the landing gear. The massive bomber, weighing 55,000 pounds fully loaded, drops onto its belly. Metal screams against concrete. Fuel tanks rupture. fire erupts. If the crew is lucky, they escape with injuries. If they're not lucky, the entire bomber explodes on impact, and it kept happening. The official explanation was pilot error. These men were careless. They needed more training. They needed better discipline. Some senior officers suggested that the new generation of pilots simply wasn't as good as the veterans. The pilots themselves were baffled and demoralized. These weren't rookie mistakes. These were experienced aviators, men who'd logged hundreds of hours, who knew these aircraft intimately. Squadron leader Basil Howe of the Royal Air Force, a man who'd completed 27 combat bombing missions over Germany, was training American pilots at Wright Field. He knew aircraft, he knew combat, and even he couldn't explain why this kept happening. The numbers were staggering. Hundreds of aircraft were being destroyed in these accidents. Not hundreds of incidents, hundreds of actual aircraft losses. Each one represented months of manufacturing time, thousands of man-hours, precious aluminum, and other war materials. More importantly, each crash meant dead or injured air crews. America was pouring everything into building its air armada, but they were losing bombers on their own runways at a rate that, if continued, would cripple the war effort. Lieutenant Alphonse Chapanis reported to the Aeromedical Laboratory and was assigned to various projects related to flight safety. He worked on evaluating luminescent materials for cockpit displays so pilots could read their instruments at night. He tested optical distortions in aircraft windscreens. He developed charts to help pilots recognize the symptoms of anoxia, oxygen deprivation at high altitude. He studied night vision, dark adaptation, field of view, and depth perception. All important work, all necessary. But the crashes continued, and Chapani couldn't stop thinking about them. The official explanation, pilot error, didn't make sense to him, not from a psychological perspective. When multiple highly trained individuals make the same mistake repeatedly under similar conditions, that's not random carelessness. That's a pattern. And patterns have causes. He requested permission to investigate. His superiors were skeptical. What could a psychologist contribute that experienced pilots and engineers hadn't already figured out? But they were desperate, and they gave him access to the crash reports and permission to interview the surviving pilots. Chapani began methodically. He read through dozens of accident reports. He interviewed pilot after pilot, and a picture began to emerge. The crashes almost always happened during the final approach to landing or immediately after touchdown. High workload moments. Moments when pilots were tired, when they were managing multiple tasks simultaneously, when their attention was divided between looking outside the aircraft, monitoring instruments, communicating with the tower, and operating numerous controls. Every pilot described the same thing. They had reached for one control and activated another. They had meant to adjust the flaps. They'd retracted the gear instead. Some of them didn't even realize what they'd done until they felt the aircraft settling onto its belly. Then Japanese did something that sounds obvious now, but was revolutionary in 1943. He went and looked at the cockpit, not at technical drawings, not at maintenance manuals. He climbed into actual B-17s and sat in the pilot's seat. He looked at where the controls were located. He tried to imagine operating these controls after hours of flight, exhausted, under stress, possibly injured, knowing that one mistake could kill everyone aboard. And he saw it immediately. The control for the landing gear and the control for the wing flaps were identical toggle switches, positioned side by side, operated in sequence during landing. They looked the same. They felt the same. They were right next to each other. In the stress and complexity of landing a 4-engine bomber, with everything happening quickly, with the pilot's attention divided among a dozen tasks, it was incredibly easy to reach for one switch and grab the other by mistake. Chapani checked the maintenance records and accident reports for other aircraft types. The Douglas C-47 transport, for example, had landing gear and flap controls that were completely different designs, positioned far apart in the cockpit, and operated in distinctly different ways. C-47 pilots were not retracting their wheels on landing. The problem was confined to aircraft where the controls were similar and positioned close together. This wasn't pilot error. This was design error. The aircraft were designed in a way that practically invited mistakes. Now, you have to understand how radical this conclusion was in 1943. The prevailing philosophy was that machines were engineered correctly, and humans needed to adapt to operate them. If a pilot made a mistake, the pilot needed more training. The idea that you should change the machine to accommodate human psychology was barely considered. Nimttz was proposing something that challenged decades of engineering practice. But he had data. He had pattern evidence. He had a clear explanation for why these crashes were happening. He presented his findings to his superiors at the Aeromedical Laboratory. Some were skeptical, others were intrigued. But everyone agreed on one thing. If he was right, if the problem really was the cockpit design, then the solution should be simple: change the controls so pilots couldn't confuse them. Nimttz went to work. He studied how humans perceive shape and texture through touch. He looked at research on tactile discrimination. He needed controls that would be instantly, unmistakably different, even in the dark, even when a pilot wasn't looking at them, even when that pilot was exhausted and operating on instinct. His solution was elegant. He attached a small rubber wheel, like a tire, to the end of the landing gear control lever. He attached a small wedge-shaped piece of plastic to the flap control lever. That was it. A rubber wheel and a plastic wedge. When a pilot reached for the landing gear control in the dark, his hand felt a wheel. Wheels, landing gear. The association was instant and intuitive. When he reached for the flap control, his hand felt a wedge. Flaps are wedge-shaped. Again, instant association. No thinking required. The shapes coded the function. This is called shape coding, and Nimttz had just invented it. The modifications were installed on several B-17s at Wright Field. The results were immediate and dramatic. Pilots who'd been making mistakes stopped making them. The simple tactile difference was enough. Their hands could tell them which control they were grabbing without conscious thought, without taking their eyes off the runway, without any additional mental effort. The wheels-up landing stopped, not reduced, stopped. The accident rate for this specific type of crash dropped to 0. Let me repeat that because it's important. A problem that had destroyed hundreds of aircraft and killed hundreds of airmen was solved, completely, overnight, with a rubber wheel and a plastic wedge that probably cost less than $5 total. The Army Air Forces immediately recognized the significance. If this worked for landing gear and flaps, it would work for other controls. Nimttz and his colleague Paul Fitts expanded the research. They studied every type of control confusion accident they could find. They documented 460 separate pilot errors, experiences in operating aircraft controls, and analyzed what had actually caused each one. In case after case, they found the same root cause. Controls that looked similar, felt similar, and were positioned close together were being confused under conditions of high workload, stress, fatigue, or divided attention. The solution was always the same: make the controls distinctly different in shape, size, texture, or position. Make them obvious. Make mistakes impossible. By 1904, shape coding was being implemented across the entire Army Air Force's inventory. Different aircraft types got different specific implementations, but the principle was universal. Every control that could be confused with another control was modified to make confusion impossible. The landing gear lever got a wheel shape. The flap lever got a wedge or airfoil shape. The mixture control got a shape like a fuel nozzle. The throttle got a ball or cylindrical shape, each one instantly identifiable by touch alone, and the number of control confusion accidents plummeted. Paul Fitts and Alphonse Nimttz published their research in 1947. The study, titled Analysis of Factors Contributing to 460 Pilot Error Experiences in Operating Aircraft Controls, became a foundational document in a new field. They called it human factors engineering, though it would later also be known as ergonomics. The basic principle was simple but revolutionary. Instead of forcing humans to adapt to poorly designed machines, design machines that accommodate how humans actually think, perceive, and behave. When World War II ended, shape coding became standardized worldwide. Every nation that manufactured aircraft adopted similar standards. If you walk into the cockpit of any aircraft today, from a small private plane to a massive airliner, you'll find controls shaped according to principles that Alphonse Nimttz established in 1943. The landing gear lever has a wheel shape. The flap lever has an airfoil shape. These standards are now codified in international aviation regulations. They're not suggestions, they're requirements, and they exist because of a 25-year-old psychologist who looked at a problem everyone else had called pilot error and said, no, this is design error. But Nimptz's impact extended far beyond aviation. The principles he established, The idea that you should design systems around how humans actually function, rather than how engineers wish they would function, spread into every field of technology. After the war, Japanese joined Johns Hopkins University in Baltimore, where he would spend most of his career as a professor of psychology. He continued to push the boundaries of human factors research. In the 1950s, he worked with Bell Labs on the design of push-button telephone handsets. At the time, telephone operators used keyboards with 2 rows of 5 numbers each. Error rates were high. Japanese tested 6 different configurations of buttons, evaluating speed, accuracy, and user preference. His research led directly to the 3x3 grid with the 0 off to the side that you see on every telephone today. That layout, used on billions of phones worldwide, exists because of Japanese's research. He studied how people communicate using different technologies. He ran experiments on multimodal communication before computers were common. He showed that among all possible combinations of visual contact, speaking, writing, and typing, the best performance for collaborative problem-solving always included an interactive speech mode. This research influenced decades of later work on computer interfaces and remote collaboration. He wrote the first textbook in the field of human factors, Applied Experimental Psychology, Human Factors in Engineering Design, published in 1949 and co-authored with Wendell Garner and Clifford Morgan, became the standard reference. It trained a generation of engineers, designers, and psychologists in the principles of human-centered design. Japanese taught at Johns Hopkins for 36 years. His students went on to influential careers throughout industry and academia. He consulted for private companies and government agencies around the world. IBM had a 36-year consulting relationship with him. He advised on everything from computer interface design to workplace safety. During the Cold War, he traveled throughout Europe, observing and reporting on ergonomics research in communist countries for the Office of Naval Research and the U.S. military. He served as president of the American Psychological Association's Division 21, president of the Human Factors Society, and president of the International Ergonomics Association. He received numerous honors: the Franklin Victor Taylor Award in 1963, the Paul M. Fitz Award in 1978, the American Psychological Association's Distinguished Contribution for Applications in Psychology Award in 1978, the International Ergonomics Association's Outstanding Contribution Award in 1982. But ask any human factors professional what Chapana's most important contribution was, and they'll tell you about the rubber wheel and the plastic wedge. They'll tell you about shape coding. They'll tell you about the fundamental insight that changed how we think about design. That machines should be designed for humans, not the other way around. Let me put this in perspective. When you're driving your car and you reach for the turn signal without looking, your hand knows exactly where it is and how it feels. That's human factors design. When you use your smartphone and the most common actions are in easy reach, while destructive actions like delete require extra confirmation, that's human factors design. When a surgeon operates using instruments that are shaped and colored to prevent confusion even in a high-stress emergency, that's human factors design. When nuclear power plant control rooms are laid out so that operators can't accidentally activate the wrong system, that's human factors design. All of it traces back to the principles that Alphonse Chapanis established when he was 25 years old, trying to figure out why B-17s kept crashing at Wright Field. The story of shape coding illustrates something profound about innovation. The solution to a complex, deadly problem wasn't a new technology. It wasn't a breakthrough in materials science or aerodynamics. It was a simple change in design based on understanding human psychology. Japanese didn't invent new materials. He used rubber and plastic that were readily available. He didn't invent new manufacturing techniques. Any machine shop could produce the modified controls. He didn't invent new training programs. In fact, his solution required less training, not more. What he invented was a new way of thinking about the relationship between humans and machines, and that's often how real breakthroughs happen. Not through expensive technology, but through asking better questions. Everyone else asked, "How do we train pilots to stop making this mistake?" Chapanis asked, "Why are pilots making this mistake in the first place?" Everyone else saw pilot error. Chapanis saw design error. That shift in perspective, that refusal to blame the human for a problem caused by poor design, is Chapanis's lasting legacy. There's a broader lesson here about how we evaluate accidents and mistakes. When something goes wrong, our instinct is often to blame the person who made the error, the pilot who crashed, the surgeon who operated on the wrong patient, the worker who triggered the machine malfunction, the employee who clicked the phishing link. And yes, individuals bear responsibility for their actions. But Chapani taught us to ask deeper questions. Was the error predictable? Do multiple people make the same mistake under similar circumstances? If so, the problem isn't the individual, the problem is the system. And fixing the system prevents future errors far more effectively than punishing individuals. This is called a systems approach to safety, and it's now standard practice in aviation, healthcare, nuclear power, and any other high-reliability industry. When an aircraft crashes today, investigators don't just ask what the pilot did wrong. They ask what conditions made that error possible. What design features, procedures, training gaps, or organizational factors contributed? How can we change the system so this can't happen again? That approach, that philosophy, was pioneered by Alphonse Chapani and Paul Fitts at Wright Field in 1943. Let's talk numbers. How many lives did shape coding actually save? It's impossible to know exactly. We know that hundreds of aircraft were being destroyed in control confusion accidents before the fix. We know the accident rate dropped to essentially zero after implementation. We know that shape-coded controls became mandatory on all Army Air Force's aircraft by 1904, and then standardized worldwide after the war. If we're conservative and estimate that shape coding prevented just 200 aircraft losses during the remainder of World War II, with an average crew of 10, that's 2,000 lives saved. But the real number is almost certainly much higher. Because shape coding didn't just prevent crashes at training bases in the United States, it prevented crashes during combat operations. Imagine a B-17 crew returning from a bombing run over Germany. They've been flying for 8 hours. They're exhausted. They're possibly wounded. The aircraft is damaged. They're low on fuel. As they approach their base in England, in the dark, in bad weather, the pilot needs to configure the aircraft for landing. His hands, operating by muscle memory and touch, reach for the controls. The shape coding ensures he grabs the right one every time. How many crews made it home because of that? We'll never know. But we know it was many. And remember, shape coding wasn't limited to B-17s. It was implemented on B-24s, B-25s, B-29s, P-47s, P-51s, C-47s, every aircraft type in the inventory. It continued into the post-war era. Korean War aircraft, Vietnam War aircraft, modern military aircraft, every civilian airliner ever built, every private plane, every helicopter. For 80+ years, shape coding has been preventing accidents. If we estimate very conservatively that it prevented just 10 fatal accidents per year worldwide, over 80 years, that's 800 aircraft. And, assuming an average of 5 crew and passengers per aircraft, 4,000 lives. The real number is almost certainly in the tens of thousands. All because a 25-year-old psychologist spent a week investigating what everyone else had dismissed as pilot error. Alphonse Chapani's continued his work and his advocacy for human factors engineering throughout his life. He retired from Johns Hopkins in 1982 but remained active. He published his professional autobiography, The Chapanese Chronicles, 50 Years of Human Factors Research, Education, and Design, in '99. The book is both a personal memoir and a history of the field he helped create. He recounts, in his own words, the story of investigating the wheels-up crashes at Wright Field. He describes the resistance he encountered from engineers who insisted the aircraft were designed correctly and pilots just needed better training. He explains the moment of insight when he realized that identical controls positioned side by side were asking for trouble. And he reflects on how shape coding became just one example of a broader principle. Designed for humans as they are, not as you wish they were. Chapanis died on October 4th, 2002, in Baltimore, Maryland. He was 85 years old. His obituary in the New York Times called him a founder of ergonomics. The Los Angeles Times wrote that he pioneered the field of ergonomics. The human factors community mourned the loss of one of its founding figures, but his influence endures. Every aircraft cockpit is safer because of him. Every medical device, every car, every piece of industrial equipment, every computer interface. The field of human factors engineering, which he helped establish, now employs tens of thousands of professionals worldwide. Universities offer degrees in it. Companies have entire departments devoted to it. And it all started with a simple question. Why are pilots making this mistake? Today, when you're driving and you reach for a control without looking, or when you're using a device and the interface just makes sense, or when safety-critical systems have multiple safeguards to prevent errors, you're benefiting from principles that Alphonse Chapanese pioneered. You might not know his name, most people don't, but his work has touched your life dozens of times today. And it will continue to touch the lives of billions of people for as long as humans use technology. The story of Alphonse Chapanese and shape coding reminds us that the most important innovations often come from asking better questions. Not what's wrong with people, but what's wrong with the system. Not how do we train users better, but how do we design better. Not blaming errors on human failure, but understanding the conditions that make errors likely and designing them out. These principles apply far beyond aviation. They apply to any system where humans interact with technology. And they remind us that sometimes the simplest solutions, a rubber wheel and a plastic wedge, can have the most profound impact. Hundreds of B-17 bomber crashes, thousands of lives, transformed by a 25-year-old psychologist who refused to accept that pilot error was an adequate explanation, who looked deeper, thought harder, and changed the world. If this story resonated with you, if you appreciate the incredible true stories from World War II that changed history, make sure you're subscribed. Hit that like button. These videos take extensive research to get right, and your support makes them possible. And let me know in the comments, what other untold stories from World War II would you like to see covered? Thanks for watching.